The idea today is to have this discussion to open a little bit the microphone, of course, starting from the people who will be presenting slides. Apparently, everybody has one slide set, but also to have a more interactive discussion only, let's say, rather than talk style like this morning. A moment for maybe you go deeper in what we discussed these days. Do you need PDFs? Do you need, maybe not. Or anyway, what is the role of precision for a machine that you are all aware it's supposed to be discovering with 3 events, new resonance, 9.99 TeV, and that's it, according to some. I don't think that's what we in this room. That's not the opinion that people share in this room. So it's an interesting question. We decided to approach the entire week essentially on is there a physics program that has to do with precision? Now you may say, first of all, what is precision? Precision is measuring something. What kind? How many digits? What's the impact of this? Or reaching any of them?
I disagree with that.
You disagree on that?
Yes. Precision is getting enough digits that you're sensitive to a wide spectrum of BSM models.
Okay, we have already one opinion. So other people have different standards, I suppose. Okay. So we start with Michael, and then I think we want to see the experiment, just to understand what precision can be realized in practice, at least with the present designs. And then we listen from Andrea. And in the end, we have David, who's maybe informing us a little bit on what can be done on the level of machines, different energies, beam energies, spectra, for instance, and the luminosities can be attained that, of course, all have an impact on the precision. So I leave you to this, but I'll try to, have you converge.
Okay.
And yeah, this microphone also works if whatever happens when this, or I can pass this one. Okay.
Okay.
Go.
Okay. So I'm the first of 4 presenters at this discussion, and maybe more of you will participate in the discussion, and even maybe while we're talking, please, if you have comments. So I'm the only one of the presenters who's not actually working on muon colliders. And so probably I should go last, except I asked to go first because I want to raise some issues that I have from my perspective that maybe some of you don't have. So let's just get into it. So here's where I'm coming from. So while you guys have all been working on muon colliders, I've been working on something very different, which is a proposal for the next CERN project as a Higgs factory and actually a linear collider Higgs factory. So this is something called LCF, Linear Collider Facility at CERN. Here are some references for it. So this is our 10-pager, and this is a 200-page, I guess, all the relevant things associated with that. Jürgen has been very strongly involved in this as well. So LCF is a competitor to FCCEE, and FCCEE is the CERN project according to CERN people. So LCF is likely to be discarded. But LCF has a vision which goes up to 1 TeV with precision measurements which are relevant to the Higgs program. And so if it's not chosen, there's going to be a lot of interesting physics left on the table, which hopefully a muon collider can do some or all of. And so that's more or less going to be the theme of this talk. So another thing that we have to discuss is whether there should be a low energy muon collider to take advantage of some of this physics. And the more I get into it, the more I come to a negative decision on that. And I'll present some reasons for that in this talk. But there are also reasons why you might want to really be in this center of mass region, let's say between 400 GeV and 1 TeV. And so I'll just present you some data and you guys can see what you think of it. Okay, there's one thing I'd like to say first, which is not relevant to this, but I think it is very important. In high energy physics, we, not me, but many other people, discuss precision machines versus discovery machines. And this is actually a terrible technology, a terrible terminology, because you can make discoveries with precision. However, if you listen to Kirill yesterday, it's a lot harder because the burden of proof is a lot higher. But nevertheless, we've discovered things with precision where we didn't have enough energy to get there. And then later, those were confirmed by experiments when we did get there. The W and the Z boson probably is the most prominent example of that. Now, so in this talk, I'm going to talk about discovery by resonance, which is what many people think about as discovery versus discovery by precision. Now, number two, precision at a muon collider is actually somewhat subtle because the muon collider, if you go to higher energy, still be at a lower center of mass energy. And I'll talk about that in just a moment. It can access mass scales well above the collider center of mass energy, but it's actually not so easy by virtue of what the actual cross sections look like when you compute them in the standard model. The muon collider can also allow a resonance discovery if you have some new physics that's, as Roberto said, within 1% of 10 TeV, and you can get there. And so comparing these is actually a part of this discussion. And I'm going to emphasize that in the first part of this talk. And the crucial thing is that the cross sections for these discovery modes can differ by more than a factor of 1,000. So when you try and make the precision discovery, you have the big cross sections, but at lower effective center of mass energies. But then with small cross sections, you can actually make a resonance discovery. And it's very interesting to think about which is more important when you design your program. Okay, so let's talk about that a little. So this is from one of Patrick's paper, Forsland and Mead, and it's just a table of the cross sections for Higgs production reactor. And I'd just like to point out that this is the cross section for W fusion. These are so basically there are two kinds of processes on here, T-channel processes and S-channel processes. S-channel processes are suppressed by 1 over S, that is to say 1 over the center of mass energy squared. And so as you increase the center of mass energy, the cross sections drop like a rock. On the other hand, T-channel processes, which typically are W or Z exchange processes, have not only non-decreasing, but also logarithmically increasing cross sections. And so when you're at high energy, way up here somewhere, they look very preferable because they have large cross sections and you don't need as much luminosity to study processes at those energies. However, there is something that is a defect. And I think here's another set of these slides for top quark production that Yang Ma and his collaborators published. And I think this really tells the story that I want to tell. So this is TT bar production reactions in muon colliders. Here are the T-channel processes. Here's the S-channel process, just mu plus mu minus making a top quark pair. It's dropping precipitously, even at 10 TeV, and then more at higher energies. But now you look at the mass spectrum of the TT bar pairs, and basically for all these processes, you're at 1 TeV, and only at this process are you actually at 10, or in this case, 14 TeV. So now you have to ask this question. Can I use these processes with precision at an effective center of mass energy below 1 TeV to discover new physics? Is that the best way to do it? Or is it better to find 10 events of this very subdominant process which actually directly produce the new particle? Sorry?
The ISP protection of that equal about the out.
Yeah.
With the design of the collider.
Yes. So
it's big.
It is, yeah. Right.
Also the integral of the big is a big protection.
Okay. Yeah, but here you're talking about millions of events. So if you now scale down in luminosity, assuming some luminosity evolution, maybe this is going to win for a while. So as I say, I'm not an expert on muon colliders, but this is a crucial question that you have to ask in designing your program. Okay, let's go ahead. So now Higgs coupling precisions predicted from muon colliders, at least as far as I know, are comparable to those expected from proposed E plus E minus programs. But discovery with precision, as Kirill told us yesterday, is actually difficult. And it's not just about improving the error bars. So you get 5 sigma for some particular number. I mean, look, CDF claims 7 sigma for the W mass, and nobody believes them. So you have to do more than just get your error bar small enough. And I think that's something that's built into the LCF program, and I think it ought to be built into any program, which really claims discovery by precision. And so let's talk a little more about that. So here's a table. So everything that looks like a table that I pinched from somebody else is from Forslund and Mead. These are projected Higgs precisions in the scenarios that they consider. In the right, I have projected Higgs precisions from proposed Higgs factories. So this is FCCEE, including the top quark threshold running, and LCF, basically everything up to 550 GeV. And the numbers are all in percent. And you see that they're, well, it's hard to compare left and right because on the left I did it's something that I did before with a SMEF fit, which is a little more intelligent than doing a kappa fit. But you can see that the numbers are very comparable. And so if we're really going to do FCCE before the muon collider, the numbers in this column become relevant and should probably be taken into account in the physics case. Or LCF, if that's what's chosen, produces very comparable numbers. Okay, so that's something to think about. These all depend on the integrated luminosity, the polarization in the case of a linear collider, and other details. So all that really matters is the comparison of the order of magnitude. But I just want to say the order of magnitude is very comparable, unless there's some way that you guys can really do a lot better than Forslund and Mead predicted when you go to 10 TeV.
Those are all numbers too.
Sorry?
Those are all numbers too.
What can I say? Okay, so if you have a new table of numbers where everything in the 10 TeV column is a factor of 10 better, is that true?
In kappa top.
Sorry?
Like the kappa T, for instance, you can do much better by PT bar reduction rather than DTH.
Oh yeah, I didn't include kappa T in here. The number in, sorry. Excuse me. I didn't include kappa T in this fit, but the number here is 1%.
That's percent level too, when you include just TT bar reduction, looking at the high energy.
Right. Okay. Now, comparison of PD versus RD. For the Higgs couplings in the previous table, 3 sigma is somewhere between 0.3 and 1%. So if you equate those to V squared over M squared, assuming it's coming from dimension 6 MEFT operators or the biggest things from decoupling, then you get an estimate of M, and M turns out to be in this range of 3 to 5 TeV. And if you do explicit BSM model scans, you can actually even get higher mass reach from these numbers. A recent example was published, actually the work was all done by Devin Walker and his student in a recent archive paper. So that might be interesting for you to look at. But these numbers are all within the RD range of a 10 TeV muon collider, as long as the luminosity is high enough to produce 10 events. And I guess Andrea is going to assure us that you're going to produce a pile of events. As many events as you want for this.
Okay.
Yes, that's what I'm talking about. Okay, so this observation can be used to evaluate an energy staging versus luminosity staging strategy. Let me say a little more about that on the next slide. So let's first look at the bottom of this slide. So I just decided to write down the proposed instantaneous luminosities for LCF versus muon collider. Now, I apologize, there are no projected luminosities for 550 or 1 TeV for muon collider. Tova said you can take the 3 TeV numbers and scale them by e to the 1, which means that they're smaller. And these are the numbers that I got for the scenario 1 and scenario 2 for. Sorry? Oh, okay. Okay, but I no linear scaling. Linear scale. Okay.
So
Quadratic scaling is worse.
It's
Worse.
it's worse if you go down. I
Yeah.
understand. Yes, I'm
Yeah.
saying it. So, but I want to understand why you're taking the linear scaling. I think the linear scaling, maybe some accelerator person will contradict me, but the issue with maintaining the quadratic scaling goes when you go to very high
Yes.
mass, because then you
Right.
need the beta star that is
That's
smaller and
correct.
smaller, right? Someone, okay.
Okay,
But
but
I
I'm just
think when
saying
you
I
go
need
down,
some
it's
numbers to put on
quadratic,
this
so it's
slide.
worse.
That's how I got it.
Yes. So I would say that I would extrapolate with the quadratic
Okay.
for going down.
Okay, well, but see, these are the instantaneous luminosities that we're proposing for LCF. And basically it's how much can you afford in the power bill? So only with these luminosities can you get the kind of luminosity samples that we were claiming in our studies. And so starting with a lower energy machine is problematic, but maybe a higher energy machine, but taking into account the fact that your precision measurements are done effectively at a lower center of mass energy, that might be a winner. And you guys can figure it out. Okay, so now let's go on to the next topic, which is what are the goals of the LCF program for ECM greater than or equal to 550? And those are described in this long paper, which actually has some interesting things in it. So you might want to take a look at that. So our main goals are the following. Number one, we want to confirm the Higgs coupling measurements that we did in E plus E minus to ZH in WW fusion. And this is something I referred to before, that if you see an anomaly in precision, there are a very large number of reasons why that could be wrong. And so you would like to confirm that observation in an independent process with different systematics. And I think this is something you want to think about whenever you think about a discovery with precision. So our idea is that we compare the E plus E minus to ZH with the W fusion. And if we find the same anomalies in both cases, that's a much stronger case that it's actually a real phenomenon. Secondly, we want to measure the Higgs self-coupling in Higgs pair production. And I remind you that the FCCEE plan is to measure the Higgs self-coupling by doing some very complicated SMEF fit. It's actually more complicated than you can imagine because there are some dimension 6 top quark operators that come in, which are only determined if you have the ultimate precision on the Z boson. So I'll show you how this looks like in direct double H production in a coming slide. Thirdly, the measurement of the top quark Yukawa coupling, which I think is an incredibly important measurement to be done with as high precision as you possibly can, because that's where what we say in the US, that's where the rubber meets the road as far as how does the Higgs give mass to the top. And finally, the measurement of the top quark electroweak couplings. Well, this seems not to have much to do with Higgs, but actually it has an enormous amount to do with Higgs, because if you have a strongly coupled Higgs sector, the top has what's called partial compositeness. And this typically leads to large anomalies in the TT bar Z coupling, which are observable, and so you really ought to look for them. And in particular, there's some general analysis that you should do here with dimension 6 parameters that involve time. So let me just show you a couple examples of this, which I think you might find interesting, and then I'll turn it over to somebody else. So here's the Higgs self-coupling story for E plus E minus colliders. I must say it's really interesting. So what's the problem with measuring the kappa lambda in in any circumstance from double Higgs production? Well, you have some standard model diagrams that don't involve the self-coupling, and you have standard model diagrams that do involve the self-coupling, and you add them and square. So there's possibly constructive or destructive interference depending on the values of those diagrams. And something that's interesting for a lepton collider is that there are two different processes by which you can measure double Higgs production. One is L plus L minus to ZHH, and the other one is L plus L minus to nu bar, so W fusion to HH. And interestingly, the first of those has constructive interference, and the second has destructive interference. Also, by the way, the process glue to HH, which will be used at the LHC, has destructive interference. E plus E minus to ZHH is kind of an exception to the rule. So what's plotted here is the error on kappa that you expect from the experimental program for these various processes. So if you have a process, this one, with constructive interference, there can be a 0 in the cross-section, but it occurs at a negative value of kappa lambda. So you would get this curve as a function of kappa lambda. If you have a process that has destructive interference, that has a 0 in the cross-section as a function at a positive value of delta lambda. So the standard model is this line here. This is, well, I'll show you the LHC in just a minute. Now, if you observe both of these and you add them up or combine the data, then you get something which is an estimate of the delta kappa lambda, which is very uniform in kappa lambda. So you can really believe what you think the value is. And if you're only stuck with one of these processes, then you just have to hope that kappa lambda is not in a place where you're very insensitive to it. So once again, this is the E plus E minus to ZHH at 550. This, the solid line is the nu bar HH at 550. The dotted line is when you go to 1 TeV. So you see it becomes a lot more powerful. And then when you combine everything, you get the green curve. And then from my colleague Tim Barklow, I got this interesting curve, which basically adds the Hadron Collider. So this is the new Atlas projection for HLLHC on the same scale. This, let me get them straight. This here is this bumpy green curve that I just showed you. If you do this with a photon collider, actually at 280 GeV is perfectly sufficient. You get this red line here. And then, FCCHH is the red line. And the photon collider is this solid line here that's very hard to see. And if you add up the photon collider and the E plus E minus, you get the blue line.
Standard model as well.
Sorry, standard model is 1. Yeah. So, but you know, what we're thinking about is, sorry?
The peak side is in the basic.
Yes, the peak is in a different place for every process. So the more processes you measure, the more you learn. But it depends what, you know, the real world value is. But if you expect a first order phase transition, for example, in the Higgs sector, then you're looking at values around 2. So this region is actually quite interesting. Okay, good. Let's go on to top quarks. So what we're expecting is that with these very large data samples at relatively low energies compared to the muon collider, you can measure the top quark Yukawa coupling to 3 or eventually to 1%. The TT bar Z electroweak couplings, I'm sorry, that should be an actual R, not a whatever it is sign, excuse me. With 4 inverse attobonds at 550, you can get the right-handed TT bar Z coupling to 1% and the left-handed one to 0.1%. And this, you use beam polarization for that. So that may or may not be available to muon collider. The chiral is really interesting because different models differ. in what that ratio should be. I say here the proper context for this study is SMEFT. We'll talk about SMEFT in a minute. So here's a figure that's in our long paper. This is the ILC precision that I just quoted, that little ellipse. Here's a collection of mainly Randall-Sundrin models, although the littlest Higgs model is here as well with the predictions. Let me just say that every point on this diagram is consistent with current LHC constraints. Okay? So if you can actually make that measurement, you learn a lot in the class of models that have a partial top composite. Okay, now let's talk about SMEFT. So the previous thing was a 2-parameter fit, but in SMEFT, there are many more parameters. There are actually 16 dimension 6 operators that specifically mention top. There are 7 operators with 3rd generation quarks and leptons. There are 9 operators where phi is the Higgs field. So you communicate with the top part through the Higgs field. And 2 of those contain B, and they're strongly constrained by precision electroweaving. So 16 with 2 of them obeying strong constraint. Those of you who are familiar with this in LHC, here's the similar list. And let's just go on to this. So this is a paper by, actually it's the Marcel Voss group. And Marcel is also an expert in top quark and Atlas. So he's very interested in what we're going to learn in addition to LHC when we go to a lepton collider. So HLLHC is the second red line. ILC 250, you see you don't learn very much. But when you get to 500, when you get significantly above the top quark threshold, then you begin improving these very strongly. And now there's a problem, actually I should have mentioned it on the previous slide, that you can have new physics in this vertex, or you can have new physics in a dimension in a 4 fermion contact interaction. And if you run at 1 energy, 1 center of mass energy, these are degenerate. So you have to run at 2 center of mass energy. So we propose 550 and 1 TeV to separate them. When you do that, you can measure the 4 fermion couplings, which appear here, to a very high level of accuracy. So actually, there's a quite interesting program where you basically measure the whole suite of dimension 6 SMEFT contributions that involve the top quark. Everything I've shown you here requires 4 inverse Aldebarans of data at 2 different energies and beam polarization. So it's non-trivial how this translates to muon colliders. But if you know that there's interesting information, then we can figure out how to get it. And so that's my conclusion. There are important opportunities for discovery with precision in the center of mass energy region between 400 and 1000 GeV. These have been studied in detail in E plus E minus colliders. The best results depend on the use of beam polarization and S-channel production, which requires relatively low energy. Some, but not all, of these precision discoveries are enhanced at higher energy muon colliders. In particular, anything involving W fusion, you can do it better at a muon collider by going to higher energies. But the question is, can we figure out how, for example, with Pokemon, you can collect them all? And I think that's an interesting topic for discussion at this workshop. So thank you very much. Questions?
I may have just one clarification. These 4 and 8 Attobarn, how much they used to be in the previous Snowmass and
I'm sorry?
4 and 8 inverse Attobarn you're quoting for 550 and 1 TeV. I think they used to be a little less.
No, actually at Snowmass, those are the numbers that we put for Snowmass.
I mean, in the
So the important point is that the luminosity at a linear collider, so muon colliders, we had this controversy, but for a linear collider, the projected luminosity increases linearly with the energy. So 4 inverse Aldebarans at 500 or 8 inverse Aldebarans at 1 TeV takes the same amount of time. At Snowmass, it takes more than 10 years to do each of those programs. For LCF, we can have a higher power bill, because CERN has that. So it's 7 years for each of them.
Okay, I was just comparing to all the click numbers where I don't think 8 was ever a thing, but
Okay.
I think the
So-
message
so
is
that's-
clear. We need to maybe listen later from David what he thinks about changing the luminosities we discuss currently for muon colliders at lower energies.
So maybe to quickly add on what Mike had said, when you look at the LCF document, actually what is different is that now they assume 8 inverse autobahns for 550 GeV because yes, there was a feedback loop with the people working on superconducting RF cavities, and they told us that you can reach a factor 2 higher quality factor for the cavities than anticipated like 10 years ago. And that means for the same power, you get twice the luminosity.
Yeah. Yeah. So if you look in that document, there are various, there's something quite definite that we'd like to do for the first stage. And then after that, there are lots of options. And I think between Daisy and Slack, there's a lot of controversy about what the best option should be. But fortunately, we don't have to make that decision for another 10 years in the future. So we can really figure it out. Okay, other questions?
Yeah. Anything quick?
So, Michael, the one slide you had about the SMEFT estimates and then your paper with Devin recently, because I remember that one, like the maximum point you get up to is 7 or 8 TeV in terms of getting an effect that you measure still. So that one slide you had with the partial top compositeness, since it just had a percentage deviations, not actually effects. I mean, sorry, not the scales of the particles.
So this one?
Yeah.
Yeah.
Are any of those above the 10 TeV scale? I mean,
I'm sorry, I don't know. All these are above the 5 TeV scale because we took some old rendition of this plot, and it turned out that a lot of the points were ruled out already. So we moved all the resonances up above 5 TeV. But I don't know how far above. I think in general, all the resonances here are pretty close to the 5 TeV scale.
okay, thanks.
Okay, but it's 1 over m squared. So you see, you can bring it down by a factor of 4, and you still have a lot of information that you're getting.
The question, maybe I would add to that. Are these then in the direct reach of a 10 TeV? I suppose so, yes.
Sorry?
Are the states responsible for discoupling deviations in the reach, how you call it,
I think
reach
the
discovery?
ones on this diagram are within the reach of HLLHC, except we haven't done HLLHC yet. So
Even HLHC?
yeah, the outer ones are within the reach.
The outer ones,
HLLHC.
the other one. Yeah,
But if you look
I
at
wanted
that
to make a
precision and you
statement
put
on
it
all
in
of
the
them.
center, it goes well beyond HLLHC.
Might be the case that are all below 10 TeV. That's what I was trying to get at.
But the actual numbers here are all, the resonances are 5 or 6 TeV.
I incidentally just asked this question to Patrick before, but since you brought up collecting them all, what would we be missing if we did LCF or ILC 250 and then just a 10 TeV muon collider as opposed to going through these various steps?
Well, okay, so let's put that slide up again. Okay, so as I said, here are the important goals. So any time that you can measure the Higgs couplings in WW fusion, you can confirm anything that's been seen in another process. And so a muon collider can definitely do that, as Patrick has already explained to us. The second one, the advantage here is having 2 complementary reactions for double Higgs production. And so the question is whether you have enough luminosity to do the E plus or mu plus mu minus
the ZHA, yeah.
which is an S-channel process. So the cross-section actually falls off. The third one, Patrick said you can do that comparably, probably using W fusion reactions. W fusion actually hasn't been really studied in E plus E minus. There's some old studies from the 90s, but people kind of dropped it. But it's actually really interesting at high energy because there's destructive interference between the standard model and the Higgs diagram. So the higher energy you go, the more sensitivity you have. And so you can really measure the top quark Yukawa coupling quite well as long as you're in the effective field theory. And then finally, the electroweak couplings. I think there are probably ways to do that. But as I said, when you think about it in the full variety of SMEFT, it's a sophisticated business. We make strong use of beam polarization. So you have to measure basically all the angular distributions in the final state to compensate that advantage. Okay?
I think we are close to have a complete fit that maybe we also put on the strategy for the top. I think we have everything already on the strategy concerning the last bullet, no? And two things maybe. Beam polarization are not particularly needed because you can benefit from electroweak radiation, which is chiral.
Yes.
See, as it's chiral, you can define observables which trade differently left and right.
Absolutely.
So we don't miss that part much.
But as I say, it needs to be shown. I don't know of any study that's actually available.
There are.
That says
Thursday.
And yeah, and then also the key advantage, of course, is that at 10 TV, those operators that grow with the energy, we can probe them at a scale which is 10 times higher than 1 TV.
Yeah, well, of course, the real advantage is that using the resonance discovery, you probably
no, just the contact, just the contact interaction.
Yeah.
Just the fact that it grows.
Yeah. So, I mean, another question that I asked at the beginning, I'm going to ask it again, is for any model that you can discover with precision at a 10 TeV collider, could you just discover it by discovering new particles?
No, because I will show you.
Okay, I look forward to it.
Just confirmed with the speaker that Thursday next week we discuss this fit, entire fit. Should go away by sun.
Yeah, just have to. Okay.
Now it's cool.
All right. Great. So I was asked to give a talk about the Maya detector, and maybe a bit more broadly, the detector challenges at a muon collider. So I think, as with every other part of the muon collider, right, the main challenge we have in the detector is that muons are unstable, they decay. And in the detector, what that means is you see a huge beam-induced background from decaying muons. And so you really have to design a detector that can accommodate that background and do studies to ensure that you can still do physics, both discovery physics and precision physics. So the community has been studying two designs for a 10 TeV detector, Maya and Music. I work on Maya. I'll tell you about Maya. We can also talk about how Music differs from Maya if people have questions. But we both presented results for the European strategy process a couple months ago. So I will just give you a rundown of the detector design, those results, and then discuss some of the things we've been doing in the last few days to try and improve things in real time. So there will be, even if you have already seen all those plots, there will be some very new things at the end. Okay, so I said the BIB is the main experimental challenge. So if you think about muon beams entering the detector, they're decaying. The main background is just from decaying into, TeV scale electrons. If you sum up, how many of those electrons are going to enter your detector, it's on the scale of an EeV or a million TeV, which is not a unit we like to deal with in particle physics and in collider physics. So the solution that we've adopted for the detector is to surround the beam pipe in a tungsten nozzle. You can see it here in kind of gray. The high energy electrons will shower as they pass through the nozzle. They get converted into this cloud of really soft, low energy, mostly photons, electrons, positrons, also neutrons, kind of moving around randomly. As this picture shows, this is a huge mess. This is also only 0.0003% of a single bunch crossing. So this stuff is going to be everywhere in the detector. and we have to deal with it if we want to do anything. Exactly. So they're not. They're basically all less than a GeV, and many of them are going to be out of time as well. They're still going to be depositing energy in the detector, but those photons, after passing through the nozzle, will be very low energy. And while many of the photons will be in time, a lot of the other particles will be out of time. So we have handles on dealing with them, but we have to do detailed simulations, work closely with the MDI designers to make sure that we can handle this. So if you have questions about the MDI, I mean, I think there have already been presentations about this. Also, we'll direct you to Daniele over there. But they provide us input with Fluka, and then we overlay it on a model of the detector in Geant to do studies. And it's been really important to keep up to date with the changes they make in the detector. So we started doing studies of Maya with an older version of the accelerator lattice. So here you can see kind of how the accelerator lattice has been evolving over the last few years. We started with this version 0.4, and then that turned out to not be very realistic from an accelerator design point of view. So we now ended up with this version 0.8, which you can see has significantly less dipole and quadrupole magnet around the interaction point, which is better from an accelerator point of view, but from our point of view means there's less bending power to deflect Bib away from the detector, which means more of it enters the detector. And if you kind of do sort of estimates from the MDI simulations, you see that it should be about a factor of 2 increase in the beam-induced background. Once you actually pass everything through Geant and do sort of detailed studies, it winds up being more like a factor of 10. And so we've kind of been dealing with that factor of 10 increase in Bib from when we first started all of this. That work is still ongoing in real time, in fact. But I just want to emphasize this point again, that to design a detector for a muon collider, you really have to work very closely with the accelerator and MDI experts to understand what you'll see. So we started from here in the last SNOMES process and the previous European strategy update. There was a detector design that was basically taken directly from Click for a 3 TeV or 1.5 TeV center of mass energy muon collider. You can sort of look at the different components here, but basically the most distinctive feature is the tungsten nozzles sticking out the side of the detector, have a relatively standard all silicon tracker, more granular, and then gets less granular further away. An electromagnetic calorimeter that's kind of very similar to the CMS high granularity calorimeter being built for HLHC, silicon tungsten. A hadronic calorimeter that's kind of very similar to the Atlas tile calorimeter that exists today, scintillating tile steel. The solenoid, and then a pretty simple muon system just with the sort of iron yoke structure for returning the magnetic field, because the solenoid is sitting between the calorimeters and the muon system. So I would say that overall, this made relatively conservative technology assumptions. It was effectively just the Click detector with the nozzles added and some slight reoptimization done. And that was used to do studies at 3 TeV. But I think we wanted to update this to 10 TeV. And so both Maya and Music started from that detector, and I've kind of started to go in slightly different directions. So for Maya, you can see here a really nice 3D rendering of it. The main change is that we moved the solenoid inside the calorimeters. So we went from an Atlas-like magnetic field configuration, we went from a CMS-like magnetic field configuration to an Atlas-like magnetic field configuration, where the solenoid sits between the tracker and the calorimeters. There are a couple of reasons for that. The main one is that by having the calorimeter, or by having the solenoid material there in front of the calorimeters, it provides shielding. Because now any beam-induced background particle coming off the beamline has to pass through the solenoid in order to get into the calorimeters and deposit energy. So less energy from background will be deposited there overall. Now that does mean that you'll have slightly worse energy resolution because there's extra material there, but Atlas works like this today and seems to do all right. So there's every reason to think that the same would be true at a muon collider. Also, we have increased the strength of the magnetic field to get more bending power for high PT tracks. But because the solenoid is now closer to the beamline, you can get away with less material overall. We've also partially re-optimized the silicon tracker. The original design had double-sided layers in the vertex detector. The idea being that, if you have two layers really close together, and a track coming, you can sort of trace back whether a track stub came from the interaction point or whether it came, was just two random particles that came in from the side. But improvements in the track reconstruction algorithms have meant that that isn't necessary. And so since those extra layers cost power and material, we were able to get rid of most of them. And then we've just made the calorimeter a bit deeper to fully contain the showers, although we in fact haven't, fully studied things like jet reconstruction yet. So maybe this is still subject to change. Okay, you can see here some more 3D renderings of the detector now with a muon, a photon, and a neutron superimposed on this cloud of sort of gold hits from Bib. You can see especially the muon sort of clearly punching through the cloud of background. That's exactly the experimental challenge that we face. Of course, here we've color-coded it for your convenience, so it's kind of easy to distinguish. And the reason that I show you these three is because these are the particle species that we've been using to kind of characterize the performance. Muons for the track reconstruction, photons for the electromagnetic calorimeter, and neutrons for the hadronic calorimeter. There's a whole reconstruction software framework that is kind of shared with the other future collider projects using this Key4Hep ecosystem, with some custom software from us to inject the beam-induced background during the digitization step. If you have questions, you can ask. There are several experts here. You can ask us about it. One thing I'll just point out is that the reconstruction right now is using the Pandora particle flow algorithm, which I think was also inherited from the E+E- experiments. And I think we have found it to be somewhat suboptimal for the muon collider environment out of the box, and are kind of still in the process of tuning it to muon collider. Yeah.
The author of Pandora is Mark Thompson.
I am aware of
So when
that.
it comes to DG of CERN, don't emphasize that it's suboptimal.
Hopefully by then we will have gotten it working in better order. Yeah. Yeah.
But I wanted to ask about the magnetic field. So CMS has its 12. So in practice, CMS has had a number of problems maintaining their magnetic field. It's not running at the design, which is fine now, 4 at 3.8, but even keeping it operational, keeping it clean, making sure that it has the cryogenics running has actually caused a lot of problems for CMS. Is there, as a theorist, I don't know so much, is 5 Tesla like realistic for something that size? Can this actually be maintained? Do experimentalists have the confidence that they can maintain something bigger than CMS?
I think it's a challenge. I would say that the statement right now is that today we probably could not rebuild the CMS solenoid if we needed to. The company that built it is out of business, is my understanding. So I think in principle, yes, but there would be challenges in realizing that field. Also figuring out, doing studies of realistic magnetic field simulations to understand what it would really look like. It would be a challenge. But yeah, maybe Federico wants to comment.
Well, you said most of it. There was a dedicated workshop with the detector magnet experts that took place at CERN maybe a year ago, something like that. The outcome was that it's sort of, there is a consensus that 5 Tesla is sort of the maximum we can do. Then we studied not parametrically, but almost parametrically, what would be the impact of having a lower field. And we could probably deliver similar, if not equivalent physics with something lower, so easier to build and maintain, etc. There is a little bit of trade-off that one has to take into account, because the lower the field, the more incoherent pairs at the IP then reach the trackers. So that it's part of the fine-tuning, if you like. But the consensus was that although there are technological and industrial challenges, 5 Tesla should be doable. Okay. So we just took it.
And maybe I should also point out 5 Tesla is considered baseline for at least one of the LCF detector proposals. So if you think about going to the Terra Z at the FCCEE, it doesn't work because of the huge event rate and all the curled up tracks. But for 250 on up, that's our standard. So, but you guys have much more background, so you have to investigate it. But we think
there are very few detector magnet experts. So I suspect it's the same people who reach the same conclusions.
Yeah, this is
I think they assume 6 Tesla, and it's super gigantic. It encompasses. It doesn't exist.
Yeah, so this is a common problem probably for any future collider detector is high field magnet. Okay. Yes, so I would say on the reconstruction, I mean, as you'll see at the end, we have been making progress on this, but it's an area where more work is needed in general to improve our and tune our reconstruction algorithms. Okay. Yeah, so now I will just sort of go through the kind of baseline performance results we submitted to the European strategy. So here you can see a bit more detail about the technology assumptions for our tracker, as well as a plot of the average hit density per detector layer. So we kind of start with the vertex barrel detector, go to the vertex end caps, then the inner tracker, barrel and end cap, outer tracker, barrel and end cap. And you can see that in sort of the innermost layer, we have very high densities, like up to 8,000 hits per centimeter squared, which sounds like a lot, especially compared to to LHC and HLHC. That, however, can be cut down a lot by adding, a tight timing cut around the beam crossing. And that's part of what motivates the sort of 30 picosecond timing resolution that we want in the detector, which is achievable today. The LGAD detectors being built for HLHC will have 30 picosecond resolution, but with much, millimeter by millimeter granularity rather than 25 micron by 25 micron. So there would still be some work to achieve that. I'll just make a few other points, that in a muon collider, there will only ever be 2 bunches circulating around the ring at a time. So our collisions will happen every 30 microseconds rather than every 25 nanoseconds like the HLHC. So yes, we'll have a lot of data in the tracker. We'll also have, a lot more time to read it out. You might still want some kind of on-detector intelligence to cope with this. That's something people are interested in and exploring. But there are challenges, but we don't think they're insurmountable. So you might ask, given all of those hits in the tracker from the beam-induced background, does that mean that you can't reconstruct tracks? But in fact, the track reconstruction works quite well. You can see here on the left, sort of track reconstruction efficiency without and with the beam-induced background overlay. And at least in the barrel, there's barely any impact when you add the beam-induced background, maybe like 1% or so lower in efficiency. Things are a bit worse in the forward region. I think some optimization of the geometry right around the nozzle is still needed, but that's something we plan to do in the future. And even the sort of track parameter resolution is generally quite good. You can see sort of PT resolution for different ranges of track PT on the right, We've also looked, for example, at impact parameter resolution, kind of consistently at the level of 10 microns or below, even for very high PT tracks. So in general, we think tracking will work quite well, even with these huge backgrounds. The calorimeter, again, sort of the technology assumptions for our silicon tungsten ecal and iron scintillator hadronic calorimeter. This plot is using the older version of the lattice where I mentioned there was less bib, but it's comparing the simulated energy density deposited per ecal layer between the original design in blue and Maya in red. And you can see that it's about an order of magnitude lower. That is because bib is getting absorbed in the solenoid. The solenoid is about 4 radiation lengths worth of material or 1 nuclear interaction length for the HCal. So this is really helping us a lot. Now, we don't do quite as well there are some issues with reconstruction in the calorimeters. In general, for the electromagnetic calorimeter, things are quite good for sufficiently high energy photons. But as you can see from the first plot in the top left, once you get below 100, 200 GeV of energy, the reconstruction efficiency starts to fall off, which is something we would like to improve. In fact, we've been working on improving. You can also see, if you look at the energy resolution, that the energy resolution is noticeably worse in the sort of central part of the detector, and of course in the transition region between barrel and end cap, and then actually gets better in the forward region. So the plots on the bottom are energy resolution as a function of energy for the barrel versus the end cap, and it's consistently lower in the end caps. And that's because the solenoid is sitting in front of the calorimeter in the barrel and not in the end caps. So there is an effect from that that is sort of non-negligible. These plots also show in green a kind of truth-assisted clustering with bib, where we use truth information to tell us where the photons really are, and then we cluster the energy deposits around them. That's not something, obviously, we could do in a real detector, but it's kind of giving us a target of where improvements to the reconstruction algorithms could potentially bring us. In particular, we're really not taking cell timing into account at all when we do clustering. And since I showed you before, a lot of the bib is out of time, so there could be really significant gains to be had there. It's something we're kind of interested in exploring in more detail.
Expect there will be a lot of out of time occupancy. I mean, if you're saying you want to use the timing, that's supposing that there's going to be a lot of occupancy.
There should be. So like I'll just go back to this plot. This is kind of the arrival time of particles of different species in the detector. You can see, I mean, a lot of it is far outside the time window.
So this is something we're looking, right now we do cut at like -5 to like 20 or so nanoseconds for like, say, calorimeter hits. But incorporating timing information into like the reconstruction is we're actively exploring.
In particular, you can see that when you're talking about the calorimetry, the individual particles that are going to cause the most trouble are the neutrons, because they're the only ones that have any real significant amount of energy. And those are especially out of time. So while some of the other particles are really peaked around this is a very large, if you wanted to see the interesting features that are in the other backgrounds, you have to zoom in a lot more than this. And then there are interesting features. They're not simply peaked at 0, but the neutrons are not even peaked at 0. So orange.
This band,
Yeah. So when you're talking about like total energy deposition, the time, even coarse grain timing can do a lot for you because the neutrons are so out of time and they have the most energy.
Yeah, I'm just here. The universe coming from the beam interacting with
it's from the electrons from the muon decays interacting with the nozzle through sort of complicated showers.
Yeah.
Electrons passing through the nozzle, disrupting nuclei and creating high energy.
So it's mostly photonuclear interactions. So you have photons in the broad spectrum. So you have everything from the delta baryon resonance to the giant dipole. So you produce a lot of neutrons at all energies.
Do the nozzles stay in some sense activated in the beams?
So the activation is minimal because the activation is normally given by primary hadrons interacting in the helio of, I don't know, LHC. You have a certain amount of activation, but it's negligible in comparison with, for instance, the magnets.
Okay. So, yes, so that's the ecal. Just to say that what we have seen up until, I guess, the past 48 hours is that the hadronic calorimeter things are significantly worse. So these plots are actually with the older lattice where there was less bib to start. And you can see a couple things that seem suspicious looking at neutron reconstruction. First is that in some cases, the efficiency is higher with bib than without bib, which implies you're just clustering random bib hits together rather than a real neutron. Also, you can see there's a huge gap in energy resolution going from without bib to with bib. And this was with the older lattice. So when we looked at this with the newer lattice, things were even worse. And we've been trying to understand exactly what was going on. So in that spirit, in the last, I guess, 5 minutes or so, I just want to say a few things that we've been doing, while we've been here at this workshop. So one thing is that it turned out there were some geometry overlaps in the detector model, which can lead to strange behavior in GEONT. We fixed those. Another thing is that the sort of physics list for doing these kind of low energy nuclear simulations in GEONT around the nozzle, we've gone to a more precise physics list from QGSP BERT to QGSP BERT HP. I've linked here some more slides that have more details on exactly what this entails, but essentially this is significantly more realistic. And so we think that it should better model what the bib is actually doing in our detector. So with these fixes, the amount of bib has gone up again in the tracker. We're now up to something like 20,000 hits per centimeter squared in the innermost layer. And you can see there's more everywhere, which is potentially a problem. But if we look in the calorimeter, the neutron energy deposits have gone down significantly. So the plots at the top are kind of the previous setup. The plots at the bottom, were just made on Monday. And with the fixes. And what you can see overall is that the orange is the component of energy deposits from neutrons, and it's basically vanished until you get kind of very far away. And even there's still less than there was before. So there should be less bib leaking into the calorimeter now, even if there's more in the tracker. So another thing we discovered is that so one thing we have in our reconstruction right now is a set of variable cell thresholds. We had set a higher threshold on the parts of the calorimeter that had more bib from photons, essentially. It turned out that those thresholds were all being multiplied effectively twice by the sampling fraction of the calorimeter. So, this effect was kind of getting washed out, and all of our thresholds were a factor of 42 higher than we thought they were. So obviously that will hurt reconstruction efficiency. So for example, if you look even at the photons, which looked okay, compare the sort of true energy to the energy after running GEONT, you can see it lines up relatively well. But before this fix, if you looked at the energy after digitization, it was only like capturing 70% or so of the photon. Now, after fixing everything, it's kind of back to 100%. And we saw similar improvements when we did this with both pions and neutrons as well. And so we haven't yet rerun samples with bib, but if you look kind of just at neutron energy resolution now, even without bib and the sort of central barrel and end cap, things are starting to look maybe a bit better. So we're going to do that. I think the hope is by the first week of August, there will be a US muon collider community meeting. Kind of hope to have updated results by then, so stay tuned. And then, of course, there are many more topics that we haven't gotten to yet that need more study in the detector. Probably many of them have impact on sort of thinking about precision. We haven't really looked at the muon system at all because it's so far away. Basically, no bib makes it there. But still, we'd like to think about what we could do with the muon system. The forward region needs optimization. Also thinking if we can do anything with sort of very forward produced muons would be a challenge experimentally, but could be really powerful if we could. We discussed the feasibility of the 5 Tesla magnetic field. I think that is a question. The whole readout kind of approach needs more thought. Since the collisions are happening so infrequently, you would like to read out every bunch crossing, but probably many of those collisions are still not going to be that interesting. So you might not want to write them all to disk. You probably don't want something like the LHC trigger system, but you should think about exactly what to do. Reconstruction algorithms improvements, how to measure luminosity, lots of open questions, places for more studies. So yeah, that's it. Thanks for your attention.
Questions?
And I was just curious, because I feel like something we haven't talked about much is for Maya and music. Like when we move the calorimeter on the inside of the, sorry, not the calorimeter, the solenoid on the inside of the calorimeters, we see that impact in the energy resolution of both the ECAL and the HCAL. And there's that strong dependence on like the transition region and the solenoid. So has music run into the issue that they just have way more bib in the calorimeters? And have you seen like which, in terms of the competition of where to put the solenoid, do you feel like Maya is still feeling confident in the solenoid position that like we've chosen?
Well, speaking on behalf of Maya, I would say yes, but I think that having two different designs is really important at this stage, right? So we can both continue to optimize these things and see how it goes. So, sorry. Yeah.
Also, like I'm on CMS, so I don't really know how it works at Atlas, but how does the energy resolution dependence on the solenoid look there with the more Atlas shaped design with the solenoid?
It's very complex because
Yeah.
you could do a fairer comparison if you had the same technology, right? But music, CMS, you are using crystals. Homogeneous calorimetry is much better in general for energy resolution. Atlas and Maya are using a sampling calorimeter, so worse, sort of by design. Of course, there are pros and cons, right? So to give you a quantitative answer, I think we should swap out the technology and run the option and do a fair comparison.
They should put their crystals inside the magnet.
Yeah.
Yes, music has the crystals inside the magnet, yes. Say that.
Thanks, Fede.
That's what it's called.
No, no.
I have a question on in the beginning when you were talking about the occupancy that you were measuring that was like factor of 2 higher with Fluka, but then 10 higher when you use Jayon. What's sort of going on there?
So that's a good question. I mean, I think, well, I don't know if Fede or Daniele want to comment directly on this, but I mean, some things that can happen, for instance, is like if Fluka is just counting the number of particles entering the detector, it's not necessarily counting the number of times those things interact with detector elements. If you have a very low energy particle, for example, that will make like a loop in the tracker, can interact multiple times.
The visual you have of the bib, because you can see these like.
Oh yeah, this. Yeah. Yeah, so I think like the number of particles may have only gone up by a factor of 2, but that doesn't mean that the detector activity only goes up by the same factor.
Yeah, so just to make it clear if it's not obvious, those blue lines are not coincidentally horizontally traveling electrons. They are helix
Right.
paths. They're helical paths that intersect with the tracker if they go through it, they happen to be aligned with the layer over and over and over and over and over and over. Thank you.
Did you want to add something?
The problem is, I mean, with KUKA, the scope is not to do occupancies. This would not be the best program to do it. I was also trying to see what happens inside of the detector's volume, but still, even if you consider fluencies, which are agnostic unit of measures, we don't see the factor of 10. So it's really what you were saying is really the number of hits that you can get, which doesn't translate necessarily in a higher fluence overall when you look at the global picture. But we are working to understand what is the problem. But I just wanted to add another comment. At the moment, this is Monte Carlo studies. So a factor of 2 is just the Monte Carlo uncertainty that I would imagine when we translate this in a more realistic engineering solution. So the most urgent part in my opinion, is not maybe to improve of a factor 20% more the occupancies, is to involve the engineers and get some opinions of if this can be done, integrated in let's say, cantilever way of supporting the nozzle, etc. But still, it's a work in progress.
It could also be a bug.
That's true.
Yeah.
We already found a factor of 2 a few days ago, so.
So, I mean, you mentioned that this is mostly simulation. I mean, is there anything that needs to be done in terms of test beam measurements, demonstrators also for components of the detector that you would need in order to make progress?
Definitely. So I think a lot of well, okay, I have a slide in backup, but a lot of the sort of technologies that you would need, like fast timing detectors and so on. I mean, there are people working on them, but in kind of an experiment agnostic context, doing this sort of like blue sky R&D initiatives. That I mean, we would want these detectors with, you know, good tracking detectors with excellent timing resolution that are very granular. FCC does too, so there's, you know, there's no need for those things to be muon collider specific. I think for muon collider in particular, well, there are many things. One we were just talking about is understanding, you know, what you can do with the forward muons, how muons pass through, because the forward muons will pass back through the nozzle. And what is that muon going to look like after it travels through the tungsten nozzle? Is it going to be reconstructible? I mean, that's something we can do with Geont, but it's probably also something we could do with, I don't know, muons from the LHC or a muon beam dump or like something like that. So there are definitely places where sort of small tests like that would be helpful.
I would add that the thing that is most in the detector that's most unique to a muon collider and has no similarity to other things is the readout.
Yes.
And so, you know, when you change the interaction rate so much, the event rate so much, this by a factor of 1,000 compared to what we're used to at proton-proton colliders, you open up this opportunity for triggerless readout, but you still have so much, so many interactions with your sensors, even in a small timing window, that there's no way you can read that all out and have a cool detector, meaning one that doesn't die. So you have to start translating all of the problems that we've put into our trigger and all of this into the actual on detector readout system. And that stuff takes a few decades to design, according to our current experience for their specific applications. So something that, like, in terms of the detector R&D that's specific to muon collider, I would say that's like our easily the critical path for being ready to build this.
Just to say, after the last European strategy, there were these, there was this ECFA report prepared that looked at kind of like specific technology needs by project, and they sort of rated how important it was and how immature it was. So I have two of these tables here, but you can find more in the report, and like you can see where there is overlap between muon collider at the end, and then FCC, well, FCC-HH and FCC-EH here, and then other projects as well. So
yeah, maybe these tables were also a little bit aggressive or pessimistic. I guess a carpet statement is I think Ben said this in the talk, right? We don't think of using any technology which is particularly exotic, right? So these are evolutions of sort of the technologies that will be deployed at Illumi, which makes it somewhat closer in time than maybe things that you would need for, I don't know, maybe a proton machine where you need extreme radiation hardness.
I think the statement that one could make is that if the HLHC detectors work, this would probably work too.
Yeah, in the worst case with some trade-offs that.
Obliged to ask, since the discussions we had before, energies, of course, changes the beam, but for the rest of what we are seeing over here is gonna be reason for bigger changes than what you already see day by day, essentially.
So if you wanted a different, like to go back to lower energy, or
well, 3TV is of course another point, but we just heard the sub-TV physics, for instance.
Right. So in general, the bib itself, I mean, the energy of the bib is kind of constant as a function of beam energy, because I mean, the muons are more energetic, but they also live longer. So those effects kind of cancel out. So the energy being deposited into the detector is kind of the same. That said, how it's distributed in the detector will be different. And of course, you'd have a different accelerator lattice at lower energy. So the details would probably be completely different. I think if you wanted a detector for sub-TeV, we would probably design something differently, at least somewhat differently. Yeah, right. It doesn't, yeah, exactly.
More compact.
Yeah, I mean, just think you have showers that are less energetic, so you don't need to contain them with meters of steel.
Probably can get away with a lower, well, we had a 3.5 Tesla field before too, so
we need to know before.
You can shrink it and you can decrease the solenoid fields, but the technology that you need for everything else doesn't really change, because you still need the same to fight off the occupancy of the bib, which doesn't change dramatically. You still need all the precision timing. You still need all of the tiny feature size. You still need to have an ECAL and an HCAL that can differentiate between these beam-induced background deposits in your signal. So none of the fundamentals change. You just can shrink it, and the solenoid gets easier.
So this is probably in the report for the European strategy, but compared to a click detector with the nozzles, how well actually does a missing energy measurement work?
it's a great question. I mean, yeah, we have to, that's something we haven't looked at.
Make up something, but it's really bad if you don't have tracks, right? If you don't have tracks, it's a disaster. It's just something random from your beam-induced background energy depositions, you know, like some square root total energy type thing. If you have tracks, it's extremely easy to tell. It's extremely easy to tell what is associated to the primary vertex via a track. So if you only care about calculating MET from that, which may or may not work for what you're interested in targeting, then you can probably do a lot better when you have time to do track reconstruction. If you cared about something that does not have a track, that would somehow,
Forward things.
yeah, I mean, you could get in trouble.
Thinking out loud. So I would think that if you do a Calo-based math, but looking at objects, applying some minimum relatively tight threshold on the energy, so say, I don't know, 50 GeV, then the most purely beam-induced background produced objects will probably be below that threshold. And so probably, okay, the math is not going to be great because maybe you consider only jets above 50 or 100 GeV, but it's not going to be a TeV in variance. So that means that if you finally produce a Z prime of 5 TeV, whatever, you're going to measure its mass or these things, no problem. Yeah. So precision in these kind of things. Precision achieved. Okay. So thank you, Ben, once more. So we keep going. Now we have Andrea, who's gonna give us an overview on precision of the muon collider.
So I'll try to make it, of course, short. I thought there was a need to discuss the precision of the muon collider, the bulk of those results, which there are quite some, and also to point you to some references, like the last strategy report, I think, is very comprehensive. And so especially if you want to look for target measurements, that's maybe a right starting point, plus discussing, of course, the various different items. And of course, having in mind the implication of this precision, which, as Michael said, is what matters at the end, in terms of BSM exploration, in terms of maybe even other questions that can emerge concerning the standard model. But okay, so does it move? No. Should I move it like this? Eh? Yes. On the mouse. On the mouse? Which mouse? Ah, on the pad. Okay. So I think, I don't know, you can disagree, of course, but I believe it's obvious that the really unique aspect of the muon collider that you will not be able to do anywhere else, for obvious reason, is the fact that you have a lot of available energy. And so if you can exploit this energy for doing precision, and you can exploit this energy for doing precision, that's something that anybody else can do, while the Higgs couplings can be done, while intermediate energies can be reached by other means. And here the idea is something very simple. Virtual effect, I'm not saying loops, just off-shell particles of very heavy new physics, their effect is boosted by the large collision energy. So the process I have in mind here are the, if you want, simplest processes, direct mu plus mu minus annihilation at 10 TeV, because they are the ones that have the highest energy, in fact. And so the fact is that since the effect of this physics, which is even heavier, which is even, so it's not in the direct reach, can weigh 100 TeV. So since you are measuring at 10 TeV, this makes that the effect of this physics is boosted, such that at the end, by making these measurements of this mu plus mu minus cross-section at 10 TeV, you can see it, you can discover it. And this is relevant both for type of electroweak physics, but also for flavor. I wanted to make, I always like to explain this, I always like to speak of this analogy with the compositeness of the proton or the neutron, the nucleon compositeness. That is an example of a fully conclusive and direct proof of the question you have been asking for, which is the finite size of the protons. Because if you ask that question, you don't need to discover new particles. What you need to do is to discover that the charge radius of the proton is non-zero. right? And the direct way to do so is to measure and compare with the standard model. And in this plot, you have a measurement and a comparison, so the points, which are compared with the standard model, which back then was the point-like nucleon prediction, as a function of this angle. And this angle is essentially the t variable. And so when you make large angle, it means you have large scattering energy. Okay, and the behavior is the one you expect. When you go to higher energies, the effect of proton compositeness, which is this new physics scale lambda of order 100 MeV, becomes enhanced, becomes big. And so you are able, in fact, to discover that the nucleon is composite only after people were able to engineer collisions of electrons on nucleons with a center of mass energy that was not as high as lambda QCD, but slightly below that. Because then doing this plot, they could go in the very high momentum transfer region where this effect become enhanced. And this to me is an extremely convincing also discovery because you can fit it very well with the theory beyond the standard model, which foresees a finite radius for the nucleus. So, so the two things I wanted to say here is that predictions, so that precision can very well be a direct and very conclusive discovery of new physics. This is one of the examples Michael mentioned and others. And the other thing I wanted to say is that it's not surprising at all that if you have larger available energy, you are sensitive to higher scale effect because the precision needs to be less. You have less, you have more easy task to distinguish this line versus this line because you are at high energy in comparison with what you have here. Okay, which has a number of benefits also in terms of credibility of the result, in terms of the precision by which you need to do the measurement, but also the theoretical prediction. If the gap is big, it's easier to be sure. And quantitatively, the formula is simply that new physics contribution to observables goes like the square of the ratio between the energy and the new physics scale. If you are at 100 TeV, new physics scale, this means that then if you measure observable at the electroweak scale, this is an effect of 1 part per million, okay, which is very, very difficult to observe. If you are at 10 TeV, instead, this becomes 10 to the minus 2. And this is a bar plot that has to do with effective operator scale that you can, if you want, interpret as somehow the typical mass of models, new physics models that have particles that mediate this new interaction, which is one of the many possible new interactions that in fact will show up in these muon collider measurements as growing with energy. This is 100 TeV, and so we have a generic sensitivity to the 100 TeV scale of or more. This is an example of what you can do then with this measurement. If you have a new massive Z prime boson, this is mass in so the order of 200s of 300s of TeV. This is decoupling, and this is the muon collider sensitivity at 10 TeV compared with lower energy E plus minus collider like CLIC, SCCHH program, and all these kind of things. And so you see the muon collider is much better, and is also very good to probe the composite nature of the Higgs. Again, we want to make like the nucleon compositeness, we want to make Higgs composite, we want to see if the size of the Higgs is finite or not, and we can do it by these high energy measurements. I was mentioning, so this was more like the Higgs and the electroweak sector. Flavor physics. There has been a number of studies in the past, which now we are collecting in a more structured way. For example, showing that if you look at very low energy and very precise searches, for example, of lepton flavor violation in tau decay to 3 muon, this is the current reach. This is the future sensitivity. But now the same effect that could show up in this very precise, very low energy, if you want, very precise, very complicated experimental setup, etc. You can test it at up to a higher scale at the muon collider or comparable, okay, with respect to future projection. This is new physics in second family, so charm up transition, and this is again the muon collider doing better. In some cases, for example, in this case, the projections are above the muon collider. But what I'm saying is that also for flavor physics type of things, this mechanism in which you target the effects which are growing with the energy, of course, it's very easy to get good sensitivity because the effects are just larger than they are with traditional low energy probes, okay, with flavor physics like meson physics, tau decay, and so on. Then there is, of course, the precision at the electroweak scale. okay, which essentially corresponds to when, for example, in vector boson fusions, the muon center of mass energy, the center of mass energy of the reactions that you're probing is of the order of 100 GeV, can be slightly above, but is not 10 TeV. In this case, you have bigger rates such that you can make these measurements at the per mil level. And so we already seen Higgs couplings determination, which are competitive with the ones you will get at a low energy Higgs factory, taking of course into account that maybe the low energy Higgs factory will come first before the muon collider. So this is very interesting confirmation, as Michael said, but it's not the unique physics case of the muon collider. There are also a large number of singly produced W and Z bosons, around 100 millions, very much like single Higgs in vector boson fusion is very abundant. There are similar processes that produce W and Z bosons. And in principle, there could be something to learn from this. However, I don't think it's been studied, right, so much. And I also wanted to mention this opportunity of forward muon tagging that has been discussed already before, because it's relevant, for example, to differentiate kappa W and kappa Z of the Higgs. So these results, I think they are the ones that are based on this capability, which will be very important to establish experimentally. Low energy muon colliders. I think Michael was alluding to the fact that when you go to much lower energy than 3 TeV or 1 TeV, then there are lepton colliders like E plus E minus that can have a much higher luminosity than the muon collider, okay? But muon collider luminosity is not competitive to those. And then in this respect, my viewpoint is that the only low energy muon colliders that are worth considering are very low energy muon colliders that are really cheap in terms of the acceleration that they don't need, like for example the Higgs Pole muon collider, which however has other challenges. And one possibility that to me is very interesting is the top threshold muon collider. The design luminosity of this top threshold muon collider, this is from old studies, enables a precise enough measurement of the top mass. I think at this stage, to me, the big question mark is whether the beam energy can be calibrated to the level that is needed, in fact, to measure this 50 MeV, okay? And this is not, of course, a priority at the moment of the IMCC, but it's a question that I think we should try to address. Last, slightly more recently than these items, there is an important arena for precision that that comes at a. Sorry, I think I forgot to put the plot. Okay, I did forget. Yeah, I did. Yeah, shit. Okay, so there is an opportunity related with deep inelastic scattering initiated by neutrinos. Because the muons in the straight section of the accelerator, they decay and they produce a collimated beam of neutrinos. And then these neutrinos have TeV energy, and so you can make them collide on a target in some sort of forward physics facility, phaser type of experiment, okay? Forward, but not too far away. And so this is an impressive statistics of neutrino deep inelastic scattering events that lead the region of the X-Q square plane that is very favorable, where perturbability be applied pretty well, where you are deeply deep inelastic scattering regime. Yep. It's not working? Okay. And so the opportunities for this type of possible experiment, of course, which is a parasitical experiment with respect to the main muon collider, I think something that in the future should be developed more. And the two things that have been studied so far are the possibility of a PDF fit, which would improve precision of the PDF enormously on a log scale. Okay, so we would like to call it the ultimate PDF fit in neutrino deep inelastic scattering, but also measurement of the CKM elements, again in deep inelastic scattering from, in fact, a combined fit with the PDF. These are some projections. Here you see the current knowledge, and well, the dot is the statistical power, and then you have, of course, what is considered realistic to do given given the simultaneous fit to the PDF and other sources of uncertainties. Okay, so more or less, this to me is the list of things that have been discussed so far about the muon collider precision. As you see, there are several items. I wanted just to add one comment concerning the what personally I consider maybe one interesting theory challenge that I not yet have the solution to, concerning this precision from energy, which again are two scale processes in which you have very high energy of the scattering, like, which is the center of mass energy of the collider, but then you also have a small parameter, which is the electroweak scale, and this acts as an infrared cutoff scale with respect to the large muon collider energy, and so it's a place where, of course, effects associated with radiation, in this case electroweak radiation, become very important. And so what we have seen already in Davide's talk is that the Casimir associated with the double logs that, sorry, the Casimir, the pseudo factor associated with this, with the double logarithm of the scale separation at the 10 TeV muon collider, once you multiply it with typical Casimir factor that you found, can be 1, and in fact Davide was finding in several cases negative cross-sectional next reading order, because this effect is clearly beyond perturbativity and in a way that it needs to be resummed. This is not only a technical complication, but it's also a great opportunity for physics. And so I don't know if you can read here in red. I've marked in this list of processes with corresponding theoretical predictions for the number of expected events. I have listed the ones which are charged final state. For example, this one is electron neutrino. Okay, and this one is E plus E minus. So this is the electron neutrino is the charged current counterpart of this E plus E minus at 10 TeV. And so the point is that this E plus E minus final state, of course, emerges from the emission of a W boson, which is extremely likely, to the point that this is 2,300 events, while the ones that correspond to E plus E minus exclusive, okay, is this one, it's around 7,000. So there is a gap, but it's a minor gap. And so by for doing physics, I can benefit, in fact, from a larger list, if you want, or interesting processes that also in particular include charged final state. Also, there is the fact that also David alluded to, of the fact that the way new physics contributes to radiation is, so new physics contribute to radiation in a distinctive pattern. And so even for the neutral final state, it's interesting to define two types of observables, ones in which you veto extra emission of vector bosons and dark photons, and the one in which we include them, okay? And the two cross sections again are comparable because the effect of the radiation is large, and so you have to compute it. But leaving aside the calculations, the important thing is that the combination of, oh, sorry, there was a question. Sorry.
This table.
Yep.
Physics-wise, I agree with you. So it's not a question of physics, but can you explain to me what exactly I'm looking at the table? I understand the exclusive versus semi-exclusive, but what are the numbers?
The number is the number of expected event with 10 inverse atoms. So it's the luminosity divided by 10 inverse atoms. Okay. So I sorry, maybe you cannot read it. This is around 7,000. This is 9,000. This is 200.
Now the reason why okay, so that is what I thought. But so naively, I would think, say, electron nu E inclusive, I can have two muons coming in, they exchange a photon, and one of them has an
sorry.
So I would have expected that
there is a cut. So
okay.
In the case of electron neutrino, of course, it's a PT cut of the electron. In the other cases, it's an invariant mass cut, which brings me, if you remember,
of what sort of scale are we talking about? TeV, hundreds of GeV?
Yeah, 80% of the beam energy. Or 60, I forgot now, but like a big fraction. So this is really studying this peak, if you want, that we have seen several times today on the high invariant mass region, which is the one that matters, because I say here I'm mostly looking for effects which are big at high energy. Okay, the highest the energy, there is a polynomial enhancement of the new physics effects that I'm looking at. Okay. So this is the reason for being in this high energy regime. And then also the thing which is a bit, so it's uncommon, it's different from QCD. So in QCD, all this type of radiation, like it's new physics independent, okay? You add it on top. It doesn't really make a difference if you study the emission of gluons, normally at least, it doesn't really make a big difference for your capability of constraining new physics. Here is slightly different because think to this, if you have a charge at final state, for example, it means that there has been a W boson emission. Okay, otherwise, for mu plus, mu minus, you cannot get electron and neutrino.
I mean, you have the color-on models, you're looking for things that.
What?
It's whether or not it's important that you're scattering gluons or quarks, and this depends on what you're looking for. Say KK gluons.
No, sorry. This is not, I'm not searching for new particles, okay? I'm searching for new effects, new interactions, okay? So new particles are heavy. Huh? Very heavy new particles.
You're very heavy, at the galaxy, this depends on whether or not I'm scattering gluons or quarks.
Sorry, no, I think we're speaking of a completely different thing. I'm saying, so I tell you what I want to say. So, so if you have, let's say, let's take an effective interaction, but this blob could be some amplitude. Okay, it can be the standard model amplitude, or there could be BSM. Okay, so what I'm saying is simply that, of course, BSM will modify in a slightly different way the neutral amplitude, which is mu e, okay? Then the charged, which will be mu nu e nu, right? There are different directions if you want in the effective field theory operator space or in the space of models, okay? And so the moment in which I emit a W boson, this means that essentially my calculation, okay, is not gonna go through this neutral vertex, but it's gonna go through the charged vertex. And so it will depend on a slightly different direction in the new physics parameter space. Another thing I can comment related to this, also the chirality of the external exit matters, because electroweak radiation is chiral. And so while in a certain process I may be confusing a new interaction with right-handed and with the new interaction with left-handed, here I resolve it, okay? I resolve the difference because the pattern of radiation is different, and so if I measure this and this, I compare, I have access to the chirality, okay? So, yeah, this is something that I find interesting in the sense that then if you look, for example, in this case, you combine the measurement in the charged, okay, with the measurement in the neutral, and of course you see the impact of improvement of new physics. In this case as well, you have these two parameters, you make these two different measurements, exclusive and, if you want, semi-inclusive, and the same thing. This is an example taken from top physics, and so you have these different bands that they interact, they intersect, and give you this. So just to say that, so this, the message just wants to be that these big electroweak radiation effects that of course needs to be computed just for the sake of a standard model and to make the prediction are also interesting because they add variety to the observables that the muon collider can measure in the first place, because you can measure the charged final state, the final state with radiation, the final state without radiation. And also, because of this proliferation of possible final states, it also helps you characterize better a possible discovery, because maybe you want, so the fact that we can resolve different interaction is not just interesting academically. It means that if you see something new in one measurement, you can also confirm it in another measurement, and at the end single out what you have seen or not. So in certain sense, the muon collider is not the classical E plus E minus collider where all you can do is E plus E minus two things. Okay, there is more. Okay, there is more. Nothing, but what I wanted essentially to bring for the discussion was this slide with I mean, yeah, with these bullets that that somehow summarize what has been discussed so far related with precision at the muon collider. No.
Maybe it's relevant for next week, but the plots you shown at the end with effective charger currents and whatever it.
Yep.
Yeah, the one on the right. So
on the right.
Yes. Does it mean that if you were to discover indirectly, so from an heavy Z prime or type blah blah, you can distinguish it from being blah 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 Z
Blah
prime?
blah 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 blah.
Different Z primes. Different vectors. You integrate.
Yeah, for example,
this is lepton
if you,
flavor
for example,
violation.
if you want to characterize, if you want to characterize the coupling of a very heavy Z prime that you discover indirectly, you can do by using combination of these measurements.
Yeah,
yes.
These are flavor violating 2, 3, 2,
So
1.
this is flavor violating.
But
yes.
The effect is there also if you're flavor conserving, I suppose.
Yeah. So this is just a random collection of examples where you see this complementarity.
Okay. So next week we have a talk on the direct discoveries of the Z primes, correct? Maybe we should think about also how you can use this kind of information for that kind of model discrimination. Yeah.
So very quick question, because I mean, if you had, let's say, I don't know, whatever sub-TeVe plus E minus collider, did you make the exercise to somehow combine the flavor complement, to try to sort out the flavor complementarity of E plus E minus measurements for such operators?
The thing is that, so yes, we can do, we did this at 3TV, everything scales down linearly, right? In terms of scale reach, right? And so in most cases, you will be less competitive with flavor, with current flavor measurements. This was your question.
No. I'm thinking if you have okay, let's consider you have a Higgs factor in E plus E minus at whatever energy, 500 GeV, 365 or whatever, where you can do similar measurements, right? Yeah. Which are probably more prominent in the 1-1 flavor directions than in the 2-2 flavor directions, and then try to get a combined fit to get the synergy from.
The thing is that this same, the vast majority of the same interaction, you can prove them in, I don't know, flavor physics, like decay, so in low energy flavor physics, okay, regular flavor physics. And so what I'm saying is that at the lower energy plus E minus, in first approximation, you can scale down all this sensitivity by the ratio between the 10 TeV energy of the muon collider and the energy of this lower energy plus E minus. Of course, the sensitivity can improve a bit if you have a lot of luminosity, but the improvement with the luminosity is clearly not linear, right? So in first approximation, we need the 10 TeV muon collider to really go to the point where you can say that somehow you are in many, we have many more plots than this, but just you look at this, you can imagine that. So at this point, we can really say that you are starting exploring, in most cases, virgin territory with respect to regular flavor physics, while with the 3TV muon collider, less the case. Okay, so the energy is very important for this type of studies, of course.
Okay.
Makes sense.
Okay.
Cioè FCC, if you want FCC here, if you like flavor.
No, the point I wanted to make was not let's say the difference in reach for certain operators, but maybe in having like both types of machines trying to disentangle flavor blind directions that would left when you only had one of the colliders.
Yeah, I understand your point. I'm doubt that if you have a 250 GeV, you do the study at 250 GeV, this bar go down, that there will be some flavor measurement that we already know, and it's better than yeah. But we haven't done the exercise.
So, questions for Andrea?
Maybe a naive curiosity. Thinking of the Higgs-Paul muon collider, how long would it take us to find the Higgs?
This is a very good question. Yeah, it's a very good question. So there is a no.
I mean, it's very narrow, right? And we have.
I'm pretty sure that I'm not. I think no. So there is a okay. So
then
people study, there's in a finite time, you can find it.
Yeah, there is
If
a
it's 10 to the 5th, no way.
so there are studies that try to do that, but as you know, the Higgs-Bohr muon collider has the problem that you need to get this very small beam energy spread, right? Beam energy spread, and if you manage to get there, then you can do some useful measurement. To me, the only useful measurement, frankly speaking, is the width of the Higgs. That I really find something that would be worth investing. While the top threshold muon collider doesn't need anything special, doesn't need to make the beam energy spread small. It's already small enough. That's why, to me, the more, yeah, no. That's an even more difficult question. I think getting to the top threshold will be very easy from the viewpoint of acceleration. Would not be a challenge. The challenge will be to measure the beam energy.
But what spread somehow would want the new collider
So the natural. Oh.
You're spoiling next talk, but maybe David wants to give you a quick answer.
Yeah, we can, it's MEV scale, so, yeah. But I have a few more numbers there. It can definitely be done. Okay.
Do you also have a number for the calibration, the perspective for calibrating the beam, the muon collider beam energy, for example, at a 380 GeV muon collider?
Get about 1/10 of an MEV.
1/10.
Yeah.
The beam energy calibration.
Yeah.
Okay, then we do the top threshold muon collider. That's it.
Oh yeah. We could do it.
Okay, then yeah, then the first stage is decided.
Then it's like they all. Yeah, no, I mean, plus minus is very like the problem and how.
Topic for dinners. So, okay, we thank Andrea once more. In the meantime, I change the slides and quickly move. I'm slowly learning.
Okay, yeah, let's see, sort of.
No, maybe not yet learning.
That working.
Okay, try again.
Oh, let me see if this works. Yeah, I can go back and forth. Good. Okay, so let's see. It's gonna hopefully it won't take too long, but there's here I'm looking at precision physics from the accelerator side. And the general idea is we have a muon collider. It's basically a lepton collider without radiation, so all the beam shrilling and related stuff that you obscure low mass leptons aren't there, and you can do significant precision at the energy level. And the idea is there something we can learn at the precision level in the low energy landscape, which means anything under a TeV, and also can we do it for higher energies? So I'm just showing here the current scenario with kind of showing the luminosity formula and sort of how things scale. This 10⁻³ for delta E over E is sort of our best guess, as we believe we can do beam dynamics in the storage ring and the collisions quite well at 10⁻³ delta E over E, roughly independent of E. So that's where that comes from, and the other things are due to the let's see, does this
You can use
a
this
pointer or not? Doesn't matter too much. Oh, no, maybe this is better. I don't trust lasers. At any rate, so basically the luminosity basically goes as a transverse emittance, but actually the longitudinal emittance goes in here because that tells you how long the bunch will be, and therefore the bunch length is gives you roughly the transverse betatron function. But at any rate, if you look here, because you can go to shorter bunch lengths as you go down up in energy, this transverse beta gets smaller with the energy. The whole thing kind of scales naturally as energy squared as you go up in energy, and roughly as you go down. But and the other thing is that in terms of storage, really goes as the average B field in the storage ring, and so that can tell you what luminosity you can get from a ring with the different energies. So, at any rate, so we start with roughly 10 to the actually, this sort of was roughly 10 to the 34th at 1 TV, and then scales up and down from there. At any rate, the muon collider, as we currently envision it, is a high energy machine, 3 to 10 TV, and sort of this is kind of layout on the CERN, in which you can see is actually a fairly small perturbation to the to what exists on the CERN site. And this is sort of a stylized picture of what it might look like on the Fermilab layout. Both of these only have a single, as shown here, have only a single collider ring, which is for the highest energy, the 3 to 10 TV. If we want to do any collisions at lower energy, we probably want a lower energy machine. Now, in each of these, the accelerator goes through various stages. You can take a beam out of this acceleration chain at any energy from hopefully 50 GeV up to the full energy, and then collide it in a different ring. For a low energy one, you probably want to do it in a new ring. At any rate, the cooling scenarios have sort of been developed, both able to get transverse emittances down to the sort of scale. This cooling sort of has 2 stages, roughly a 60 cooling, where you basically are minimizing both longitudinal and transverse emittances. So for low energy colliders, we probably want to be around here. Now for higher energy, we're able to allow the longitudinal emittance to increase, and we really want the smallest possible transverse emittance for the luminosity. Now for the Higgs collider sort of idea, for where we want really high precision on energy, we really are most interested in the smallest possible longitudinal emittances, and that's probably where we would start these medium energy, low energy collisions. The emittance after sort of the 60 coolings are shown there, and after final cooling, this is from an earlier scheme. The latest scheme is somewhat better in both transverse and longitudinal emittances, and that shows up in significantly better luminosity for the various scenarios. Now, in the low energy region, there are all sorts of things. We sort of know what's there, but maybe we want to measure some of that in higher precision. And so I show you the Z0, and well, the Higgs, actually this was originally developed before it was discovered, but the 125 Jeb Higgs resonance is there, and we can see thresholds for WW, TT, and the Z Higgs. A key advantage of a muon collider is we have a storage ring with muons, and we can actually measure the energy up of the beam in the storage ring to very high precision by monitoring the spin precession. Now, this was developed by Raja and Tolestrup back around 2000. And what you're dealing with is the fact our initial beam, while we aren't at least initially selecting for polarization. It selects more forward than backward decay, so it has an initial polarization on the order of 10%. And that actually been retained through the cooling, accelerating, and storage. So from the spin procession, we can measure the Higgs, well, we can measure the beam energy in to high precision, which then means we can measure the masses of things we are observing to that high precision. There's a caveat here that we haven't redone the precision energy measurement calculation for the current cooling and collider scenario. So that if we want to use that, we would need to redo that and make sure we are able to get this accuracy.
I can ask you something. So the point is then is whether the polarization is retained during cooling.
Yeah.
And so there has been simulations of this, or it's just an estimate? So
we had simulations of this, yeah.
So I think it's going to be true then.
But not for the most recent cooling scenario. But yeah, yeah. So that would need to be verified, and again, if we needed more polarization, we can modify the capture to have a higher initial polarization, but that would probably reduce the capture rate a bit. But that's something that could be optimized. So the idea that, well, do we want a smaller storage ring for earlier physics? And one reason would be, gee, it gets you from the operational level. We'll learn how to operate a muon collider before we built the entire thing, hopefully, and get some early physics. Actually, observing mu plus, mu minus in a collider producing something would be certainly a worthwhile first goal. Typically we're okay in this early regime. We want to look at collisions between either this would be the Higgs and the and say the top threshold, so that which would mean we would have to design for the highest energy, so that we'd need likely a kilometer circumference for that, but we could operate that at lower energy, again with proportional to energy loss in luminosity. So one of our potential goals, and which we studied to some degree prior to SNOAS, was a Higgs factory. That is, takes 62 odd GeV muons and collide them in a ring. And the difficulty is that the Higgs is there, but it's at a very narrow width of roughly 4 MeV. And to measure it with high precision, we'd like to have a beam energy spread similar to that, which would then give us a very small energy spread, which makes it, which the first order gives us a somewhat lower luminosity. But again, we've did studies of that, and it looked very possible. We at least from we came up with we could measure the width to the order of 1/10 of an MeV, and also the absolute value of the energy to that scale. Again, using the spin precession as a to assist us in that. The scan over energies to find it was also simulated. I think it's actually easier now than we studied then, because I think we will know the mass of the Higgs from just the LHC data is significantly better than we knew it thought we would at that time, and actually if a linear collider. It also has a Higgs factory. We also have that more accurately. Now, how actually really need to know those is a good question. But again, we could do measurements, and there were again of various parameters of the Higgs. I guess well, depending on the luminosity, roughly. I think we're getting about 10,000 to 100,000 Higgs per year, and running in that mode. So that's a possibility. When I was looking at this, I ran into a comment from Dave Klein, which actually he gave before the Higgs mass was discovered. He was saying, well, it should be light and it should be less than 130 according to minimum supersymmetry. And of course, supersymmetry tells you there'd be Higgs partners, or at least that's what was thought. I don't know if this is still believed, and whether what the mass of the Higgs partners would be. At that time, he was thinking, well, maybe they'll be about 400 GeV. Of course, if you had a Higgs collider or a muon collider, you could run at that mode wherever these new particles are and measure them quite precisely. The other thresholds we might want to look at are, say, W plus, W minus. If we could calibrate at least the energy of these, and to some extent the heights of these fairly accurately. This is sort of where the top threshold might be, and would be somewhere around there. We can conceivably, depending on how you convolute this, what you would be able to measure on the shape versus the top mass and the decay models. You could measure the top fairly precisely, again, from the beam itself down to the 10th MeV, but then you'd have to convolute it to whatever the shape coming out there is. But that might be possible. Of course, this sort of small energy spread and ability to calibrate it would still be true at high energy. And if we go to the full energy collider, this is a 3 TeV model. Our baseline run would be at delta E over E of a tenth of a percent, 10 to minus 3, but we could actually run with lower energy spread if you wanted a precision energy collision. And again, you might, if there was a very narrow resonance that we were exploring. So this sort of comparison of what you might get from the muon collider, and this is what you get from a light lepton collider. Beam scaling sort of messes up the sort of resolution, particularly if you could get to the multi-TeV regime, and it's less of a problem with the muon collider. But that's just sort of some of the ideas of how we might do precision, and here I'm thinking more in terms of energy, although and so again, I don't know exactly what physics there will be, whether there'll be these resonances that we'll focus on, or whether we will simply run at the highest energy and collect all the possible events. Oh, thank you.
Questions?
Thank you. Concerning the Higgs-Paul muon collider, no? Is it correct to say that it's yet to be demonstrated that this very, very small beam energy spread can really be achieved at the collision, so due to the effect of the dynamics? Because you can have this very small longitudinal emittance at the working point from where you extract the muons.
Yeah.
But is it fair to say that it's not yet been demonstrated that you can port this very small beam energy resolution to the collision because of the acceleration and this kind of things, or you think instead this been demonstrated?
We could pretty much model the energy spread. We can do rotate the beam in phase space to get given longitudinal mints, we could reduce the energy spread. Now that increases a bunch length, and then you would actually, that makes it easier. You'd have to run with a bit larger beta star, which would reduce your overall luminosity. But if you want to focus on a very small energy spread, that may definitely be worth it. So yeah, we can definitely get the energy spread small. It's hard.
I had a curiosity, in a sense. In this plane of a transverse and longitudinal, how much one has to decide before the operation of the machine where exactly you want to live? I understand some part of it really require an extra hardware, so if you want it, you have to plan for that. But let's say that I have all the hardware I need, then is there any freedom I can maybe move myself in that plane during operation for maybe reasons I understand while I operate?
Yeah, again, it's there is some flexibility. Typically, we want to go to a small, well, for the high energy collider, we want to go to a smaller usually want to go to the small transverse emits we can get, but without letting the longitudinal blow up too much. So we probably want to run toward that end. For low energy collider, if you blow up the longitudinal emits too much, you don't fit within the energy spread acceptance of the beam, so you don't want to go quite as far up in increasing the longitudinal mints to reduce the transverse. So you probably run with a, I'm thinking of this 100 to 400 GeV scale, where probably you can't use the larger longitudinal mints we're getting in the current cooling scenarios. But yeah, so depending on your operating mode. Yeah, initially we thought we'd run perhaps at the minimal longitudinal mints for low energy 100 to 400 GeV scale experiments.
I was thinking maybe one can learn some part of the calibration of the energy beams at some point and then maybe reuse it somewhere else, just about, speculation.
If you found at a muon collider that you were, let's say you thought you might be very close to running at the energy of a resonance, let's say 10%, 25%, something like that, away from the energy of a resonance.
Yeah.
Let's say it was down to a lower energy. How hard would it be using the existing collider that you had built to step to that or to change to that energy?
Oh. No, actually, it's not very hard. I mean, the final energy is just sort of you can move it back and forth by just well, yeah, have to change.
You're not ramping. I'm asking because you're not ramping in the collider ring, so I wasn't sure if that would make anything harder.
You would have to change either where you extract, what energy you extract from the previous machine, which would be a rapid cycling synchrotron. So you either extract earlier or just change the ramp so you end at the new energy you want.
Mm-hmm.
Again, it has to be less than the maximum, but
yeah, but it's not.
Yeah, it's not very hard.
Okay, cool.
No, it's.
I mean, there is ISR at a muon collider. So if there's a prominent resonance, if you go above that resonance, you see it in radiative return. it'll be totally obvious.
Yeah. Well, yeah, you know, you'll go through going above it and then.
Right, but a
and
10
seeing
TeV
it,
muon
then-
collider doesn't
then
have to
change it.
be at 10 TeV, right?
No, you can.
It can be at
If the
any
resonance is
individual
at
energy you choose.
9.5 or 4.7, you
Yeah.
can change to it. And, we hope we can, we hope we find something like that, but
Yep.
you know, we don't know at the moment. I'm hoping the theorists come up with a great idea for what's something that's really going to be there. Something like the original hypothesis of the Z naught, but good luck. That's what we hope.
Is this true in both direction? I remember stories, Frascati people that used to say, JPSI, we almost discovered, but we missed, I don't know, 7% of the energy. So if there were to be kind of a raising thing that points at 10% higher energy instead of lower, would it be like?
Well, it would be a shame if if whatever is new is above the energy you can reach, and that's true in any machine.
It's true that quickly, I don't think it's easy to imagine what scenario would be that right now at 400 GeV or so. But
what's that?
I mean, I cannot imagine right now what would be this thing to be discovered at 400 GeV that's waiting for you, and you couldn't make at 365, by the way. But it's interesting question to know how much this thing is really fixed, and that you cannot move to a different energy for any reason. Do I have any more questions? Okay. So I guess we had already a lot of interruptions, so that it then ended up being more of a, several small talks. Next week, maybe we do something a little different. In the meantime, I thank everybody who showed the slides.